We're going to move from talking about the numerical solution procedure to talking about hand calculations of expected results or trends. So we're moving to the third step of pre-analysis. The expected trends are shown in this graphic here. So the flow, we have a uniform velocity coming in. And as the flow moves into the pipe, the flow at the wall has to stick to the pipe. That's a no-slip condition. And because of that, the flow near the wall gets decelerated by viscous friction or viscous shear. And the region that gets affected by viscosity increases as you move downstream. And the region that that is affected by viscosity is called the boundary layer. And this shows the edge. This is like a sketch of the edge of the boundary layer. And outside of the boundary layer, the flow has not yet been affected by viscosity, so you have an inviscid core. Now, because the flow gets, if you think of the distribution at a cross-section like this, over here, the flow is getting decelerated, which means that in the inviscid core, it has to get accelerated to keep the same mass flow going through. And ultimately, so the boundary layers will grow, and then the boundary layers from the opposite walls will merge, and then in that region you would get the classic parabolic profile, and we will see in a minute how you would derive that parabolic profile from the governing equations. And this is called the fully developed region, or the fully developed flow. And the fully developed region, the velocity profile doesn't change. So if I go a little bit downstream, any location downstream in the fully developed region, I'll still have the parabolic profile. And if you think of velocity, if you think of a fluid element moving along like that, it's basically moving with a constant velocity in a straight line, so it has no acceleration in the fully developed region. Upstream you have what's called the developing flow. So this is the region in which the velocity profile changes from a constant to parabolic. In the fully developed region, there's an analytical solution that you can, that any introductory fluids textbook will give you. And you get the parabolic profile, and we'll see how that comes about. In the developing flow region, you don't have an analytical solution, but you can predict the length of the developing region, which is called the entrance length. So I'm denoting it as L sub E here. So this is the length that it takes for the flow to go from a uniform profile to a parabolic profile. And based on scaling arguments from boundary layer theory, you can say that the ratio of the entrance length to the diameter is proportional to the Reynolds number, and then you have a constant of proportionality. So that's something we can check in our numerical solution from ANSYS Fluent. And from this graphic, we can also say that, so we can predict what the trend of the velocity at the axis, or the centerline velocity, has to be. So let me sketch that in. So if I'm trying to sketch as I'm moving along in the axial direction, so that's my z coordinate, and I'm looking at the axial velocity at the center line, so that's at r equal to 0. And it has to start off at whatever value you specify, in our case 1, and it has to increase and then go to a constant. So I expect it to increase, and then in the fully developed region it'll go to a constant. So that's a trend I expect for the centerline velocity, and we can check this trend against what we see in our numerical solution.